Hello and welcome to another episode of The Measurement Lab. I'm your host, Elijah Carey, and today I'm joined by Greg Richardson, a longtime member of the LabVIEW R&D team. Greg, when exactly did you start in LabVIEW R&D? What year, what version was it?
I started in 1992, just before the release of LabVIEW 2.5, the first Windows and Unix release.
Awesome. So yeah, I know Greg from speaking with you and from working with you for many years. You've touched many different aspects of LabVIEW, and so it probably is worth having you back to go into other topics. But at least for today, I want to really focus in on how LabVIEW handles memory allocation and optimizes the performance of code, all the things that happen under the hood. And as you know, this was partially inspired by an anecdote from a GDevCon attendee who said 10 minutes with you to discuss those topics was worth every penny to be there. And I think, well, why not put those insights on full display? So here we are. And I basically want to give you an opportunity to talk a little bit about all the things LabVIEW does under the hood. And I guess as a starting point, can you just give us a high-level understanding of what happens between writing code in the block diagram and LabVIEW actually being able to run something?
Sure. So every time you modify a VI, we immediately run what we call type propagation. So it's looking at the types of everything, propagating them down the wire to verify that the nodes on the receiving end, the destinations, accept that type. So if you wire a double to a plus, it says, yes, I can do that. If you wire a double array, it says, yes, I can do that. And it changes its output type to an array. So
Okay.
that
So every
happens.
connector pane change, if I change the color, it's basically looking for those changes and then propagating those to make sure everything else is, I guess, syntactically valid and runnable,
Yeah,
right? Okay.
right.
But that's
So
not the
the
same as
idea,
compiling.
no, this is just type propagation. This is just kind of syntax validation, making sure that the VI is good. The idea is anything that's going to cause it not to be able to compile is flagged at that point. So the user gets immediate feedback.
Hmm.
Then we compile kind of lazily. So when you hit the run button, if the VI hasn't compiled, it will compile then. And that involves looking at the diagram, creating what we call DFIR, or data flow intermediate representation. So it creates this other model, and that model is tuned to the kinds of things we need to do in the compiler. So that's where we run optimizations. We'll sometimes do loop unrolling or break up nodes into multiple sub pieces that can be optimized better. So we go through all of that. And then when we're done with that stage, we translate the DFIR into a LLVM. LLVM is an open source compiler project that can do code generation. So we translate our DFIR nodes into the LLVM model, and then it's the thing that generates the actual machine code. And we
Okay.
get that
So
back and we store that with the VI.
LLVMs, not to be confused with large language models. This is the last step in the process that actually generates the native assemblies for that. That's the step at which things become platform specific. Is that accurate?
Yes, yes.
Okay.
There are some things that are platform specific in the DFIR layer, but the LLVM layer is where it becomes actual CPU instructions
Okay.
that
So
are
just to
specific to the
restate,
CPU.
we start by propagating, basically traversing the hierarchy of all the types, all the wires, making sure that's valid. Then it generates the DFIR graph, does that for a series of optimizations, then gives that to LLVM, which generates the native assemblies for whatever platform. Help us understand. So first off, is that happening every time I edit my block diagram? Is it going through all of those steps every single time?
Each time you run, it's going through the compile part, and each time you make an edit, it's going through the type propagation part. So yeah, every time you move a wire, or well, reconnect a wire, if you just move it you know, in space, that's doesn't impact the compiled code.
Right.
But
That'd
if
be the
you,
difference between semantic expression and like if you just change, you
yeah,
drag things, but not change the connection. Syntactically, it's the same, right?
yeah, that's just cause we understand those are cosmetic changes versus actual changing the wiring, adding nodes, invalidates the compile.
Okay.
And
So,
so
oh,
when you run, we validate that not only is the VI you're running up to date, but the entire hierarchy of VIs that it references, they all have to be up to date.
okay. And so then, as some LabVIEW diagrams, or not diagrams, but projects, hopefully become especially large, and maybe you're dealing with hundreds or thousands of VIs, tens of thousands of VIs. Are we redoing all of those activities for every piece of code, or are we smart about what we actually recompile and when?
Yeah, we recompile each VI separately. So any VIs that haven't been touched don't need to recompile again. And depending on how your VI is set, whether it's set to separate compiled code or not, if it's not, then that code gets saved into the actual VI file. If it is set to separate it, then that code is stored into our cache and we can reload from that cache the next time. So, your sub VIs don't have to recompile every time they load.
Okay, so now that we understand the compilation chain, or really everything from like the linker, type prop, assembly generation. Now walk us through and help us understand how LabVIEW manages memory. And how does it determine when it needs to allocate more memory or create a data copy? What layer in that process is determining how
Yeah.
LabVIEW handles the memory?
Um, Mostly that happens in the defer layer. So part of what we're doing in defer is um, looking at which nodes modify um, their input values and which nodes just read them to determine that data lifetimes um, and to determine how many copies of data, where we need to make copies of data. So all that is abstracted from the user having to worry about it, and we can make those decisions for them.
So talk us through what is that unique to LabVIEW? What is it about the way in which we handle memory that's novel relative to other languages, especially other languages that do memory management on behalf of the user?
Yeah, it is somewhat similar to things that happen in other languages. Um, in C++, for example, within a function, if optimization is turned on, it may reuse the same memory location or the same CPU register for multiple values through the lifetime of a function. It's doing that because it's evaluated the data lifetime to, um, you know, see which ones overlap and which ones could reuse the same spot. LabVIEW can do that over, we'll say, a broader range because LabVIEW can actually propagate this information out of sub VIs. So we can actually kind of do an optimization that crosses across a whole hierarchy of VIs, where most functional language compilers restrict those optimizations to within a single function.
And why is that? Is it just because of how our linker then knows that sub VI is being called by another, or is it help us understand how we do that?
Yeah, it's because we have extra information on our connector pane
Hmm.
that most functional languages don't have. So in C++, if you pass the address of a variable, it may not know whether that is modified or not. But in LabVIEW, we compute that and then we expose that onto the connector pane of each VI so that the caller knows what the full behavior of the sub VI is going to be and allows us to make those optimizations.
Okay. Okay. So as far as the optimizations that take place, what are some examples of how does LabVIEW decide when a data copy is necessary? And I'm pointing to that as an example of that's an operation for an especially large piece of data, might presumably take a while, especially if you're doing it a lot.
Yeah.
So in the context of this discussion, we'll assume that it's going to result in optimal performance to minimize those. And so what are some guiding principles on when LabVIEW makes that decision to make the data copy versus not?
Yeah. It comes back to that lifetime. If we can tell that, like if you've got one node that's going to read from some value and another that's going to modify that value, if we know that we can schedule the read to happen first and it will be done before the write happens, then they can use the same value because the read's not going to mess with it, and then the write can modify it. If we can't guarantee the timing between those, because the read is something asynchronous that's going to take an indeterminate amount of time, then we see that, yes, these both need to be able to access the data at the same time. They're going to need different copies because we need a copy to go to that read that is going to not be modified, and then another copy for the other node that will modify it. So
Good.
it gets into our scheduling, it gets into multi-threading. If nodes are, deterministic and relatively fast, we'll just run them in a single thread in order. But anything that may take an indeterminate amount of time, or, that includes just a loop that's going to run for a number of iterations. We consider those asynchronous, and we will break them out and schedule them separately. And so that can cause additional copies. Usually, the copies that are created by that are advantageous to do because that's better than serializing the work, being able to do the work in parallel pays off.
Well, and so your point about the determination that things happen in a separate thread or not is a good segue to talk about some of the magic we do under the hood to optimize execution across multiple cores in your machine, especially as that's become the dominant way to improve application performance. So how I guess let's start with the history, right? Because what version of LabVIEW was it that first introduced multi-threading?
LabVIEW 5.
LabVIEW 5. And that would have been, I would guess on the year for fear of like 1990?
No.
No?
Because 2.5 was 1992. So around 2000. Around 2000. Somewhere in there.
Still well before modern multi-core processors. And I guess what was the decision that drove us to do that, at a time when basically to get more performance, you just bought a faster processor? Why did we go down that route?
Because that was a time when multi-processor computers were becoming more accessible. So this is not multi-core like today, where there's multiple independent cores running within one chip. This was actually putting multiple chips onto a motherboard. So you'd have, two Intel Pentium chips on the same motherboard. And so it was to take full advantage of those, we needed to be able to run multiple threads. Before, all of LabVIEW's multi-threading like behavior actually happened by time slicing on a single CPU. So we took turns running different VIs. Now we could make them truly independent, have them running in separate threads without, interrupting each other.
And presumably that's because at the time we had customers that had, I gather that would have been reserved for, server class, higher end workstations and compute platforms where people needed it. So interesting to understand that drove.
Really needed that throughput. They could buy those more expensive machines and get it. But that was, a small number. 2 was common. Sometimes someone would bump themselves up to 4. But we didn't see a whole lot that had more than 4 CPUs.
So how technically challenging was it? I mean, given the way in which people write LabVIEW block diagrams, was it a good fit, or was there a lot of work that went into managing execution across multiple processors?
It actually fit very well into LabVIEW's execution model because LabVIEW is data flow. It wants to run whatever has data available. So it was already set up to kind of work this way. We had an execution queue and everything went into that execution queue. And then there was one thread that serviced that execution queue. Well, with multiprocessor, we just have multiple threads servicing that execution queue. And the OS would take care of assigning the threads to the different CPUs. So it came pretty naturally.
My understanding is that when writing software, when dealing with separate independent threads in software, one of the biggest challenges is communicating between those, sharing data, sending commands, etc. And so how can you help us understand how we were able to adapt LabVIEW applications and either address or not run into some of those same challenges?
I mean, it all comes back to being a data flow language. So you're defining where the data needs to go, and then we're deciding how we can break that up and split it between processors or threads. So you don't have to think about it as a programmer. We just do it.
Okay.
And yeah, that makes it a whole lot simpler than a lot of other languages where you have to explicitly decide which threads, where you're going to introduce threads and how you're going to synchronize those threads.
So actually, it'd be helpful for me to understand. I remember when 8.2 came out, we made a big splash about multi-core processors. And I know at the time it was because they were suddenly becoming the most practical way to improve performance from a hardware perspective. Were there significant changes made to the software in that time frame to better serve, there were more and more cores showing up at the time and continue to be, or what went into making 8.2 special versus the original multi-threaded algorithm that went into 5.0?
Yeah, there really wasn't a lot. The biggest thing was when we started, we were dealing with a very small number of CPUs. And we designed our execution systems to look at the number of CPUs available and create enough threads so that we could consume them. But that was a fixed determination when LabVIEW launched of how many execution threads we were going to have. Around the 8.2 timeframe, we made that dynamic because we saw that people were still running out of threads because it wasn't about how many cores there were available. It was about how much parallelism they had in their application and how many threads were calling synchronous calls where that call consumed the thread until it was complete.
Okay.
So we made it to where we could dynamically allocate more threads to match whatever parallelism they could create in their application.
So it was about that time, or in the following versions, that we kept giving programmers more and more tools and more agency to control things like processor affinity and even to have direct reference to data values and memory. And so I think now it's interesting to understand, when is it actually useful for a user to take the optimizations into their own hands and try to use some of those tools to really prescribe what LabVIEW should be doing versus letting LabVIEW automatically determine memory copies and allocations?
I guess the 80-20 rule is a common term that's thrown out of this one might be more closer to 90-10 at least, of 90% of the time you can just let LabVIEW handle it and you'll get performance that's good enough for what you need. But in those rare cases, that 10% may be somewhere around there. you may want to dig into it and try to optimize either by using LabVIEW's memory profiling to see where your time or your memory is being used up. You can look at the show buffer allocations tool to see where LabVIEW is allocating copies, and you may be able to adjust that. And then if you really can't get LabVIEW to do what you want, yes, you can go to a data value reference where one copy of data can be accessed from multiple areas of your application. But that is, from an optimization standpoint, you only need that with, the largest of buffers. We're talking multiple gigabytes.
Okay.
Or there are other reasons to use data value references, but that's more about the interaction model you want. You really want to be able to pass a reference to multiple pieces and have them sharing data. So you're not passing the data as data flow and giving everyone their own copy. You really want them to continuously be accessing the same thing.
Okay, but basically you're saying it's risky to try to outsmart LabVIEW. Is the net that they could actually hurt the performance or just waste a lot of time that's unnecessary in trying to optimize their code?
It is certainly possible to make changes that you think will make it better that actually make it worse. But largely it's a matter of time. We like to say, don't optimize prematurely.
Okay.
Write the code, verify whether the performance is good enough or not before you decide I need to dig into it and highly optimize it. We've definitely had people who have spent a lot of time optimizing something and then realized, yeah, it's not any faster. I just wasted all that time.
I'd be interested to have you help us understand, especially for those of us that have spent most of our professional careers in LabVIEW, how in this modern era, the performance of a LabVIEW application that hasn't gone through rigorous low-level optimization, which again might be unnecessary, ultimately compares with other languages and tools. I know we talked about this earlier, but I mean, I'm looking for you to dispel common myths or misperceptions about LabVIEW, largely spawned by its graphical nature and what that means in terms of application performance and the optimizations we're able to do on behalf of our users. Any common myths or common misconceptions you'd like to clear up given the opportunity?
Yeah. One of the things is when you're dealing with hardware, in many cases, the calls to the hardware are the gating factor in your performance.
Yes.
Not the computational side of it. So, yeah, first understand, what your optimal rate could even be given hardware interactions or files or network. You may find your bottlenecks are there. Then on the computation side, yeah, for raw computations, LabVIEW compiles to, CPU instructions. So it's still pretty fast. You may find that there's places where you want to turn off LabVIEW's debugging because that does add some overhead. And in computational code, you might get another 10% by turning that off. But really, it's kind of the test and measurement mantra of measure and then look at your result to determine if you need to do anything.
Well, and to go back to your original point, I think it's interesting to consider that test and measurement is unique in many ways, one of which is how coupled the software ultimately is to hardware, and typically a high mix of hardware. You might have DMIM scopes, digitizers, the actual device under test itself. And, whereas normally pure application software is going to perform as fast as whatever hardware is running on here, you have all these constraints from the outside world. from how fast you can talk to the device, or how fast it'll respond to your command, or how fast you can sample from this digitizer. And I think it's interesting to consider how important this was in driving what LabVIEW has become. And, we talk a lot about actor-oriented design, but you have all these free-running things that are talking to the different pieces of hardware. And you don't want any one of them to define how quickly you talk to any other aspect of your system, right? And I feel like that's something that may not be as well understood as I would like. And it ultimately highlights why it's so critically important that test and measurement developers have a way of dealing with all those actors, managing the performance and communication with them.
Yeah.
I know there's not really a question there, but I guess with that in mind, when you think about some of the challenges that you've personally been involved with, either from a customer's perspective or as one of the architects of LabVIEW itself, what are some of the common challenges that you've dealt with so that our customers don't have to when dealing with memory allocation, especially in really, really complex, large-scale use cases?
I mean, it starts with that lifetime evaluation, what we call in-placeness, figuring out which wires can use the same memory as other wires. And then you can get into things like, minimizing the amount of overhead from reentrant VIs. So when reentrancy was kind of first created, it copied the entire data space. It's a term we use for the area where we save all the values related to a VI, all the data values in that data space. Well, some of those.
So if something's reentrant, that means it's going to reuse that data space, or going to create a new data space?
It means each call gets a separate data space. So within that, we've done things, knew that portions of the data space weren't any different. They're not modified. They're, just initialized values, constants, values that are set once. And they didn't need to be replicated between each copy. So we've pulled those out so that they're referenced to a separate piece. So that lowers the memory overhead of each reentrant instance. We also introduced things like shared reentrancy, where we just, instead of when we're preparing to run, allocating a copy of every reentrant VI for every call site, shared reentrancy says we're going to create a few, and then each call site's just going to claim one when they need it, and then they'll release it afterwards. So
is there an easy answer as far as like a new user when they should select? This is in the VI properties menu. You can select reentrant, shared reentrancy or not. And if people are looking at it and feeling overwhelmed, can you help them understand, like, when should I use one versus the other?
In general, pre-allocated reentrancy gives you the best runtime performance because it's trading off kind of some initialization memory allocation for smoother runtime execution. Then it's just a matter of looking at your program's overall memory usage. And if you think that's high, then one of the things you can do is go in and look at your reentrant VIs and see if there's some places to insert some shared clones, some shared reentrancy to break those up. Because if you have one VI that calls a reentrant VI twice, and then in that VI it calls another reentrant VI in two places, you don't just get two copies of the second level sub VI, because for each of the two calls in the top level VI, you got a copy of the second one. So there's two there. And for each of those, you have two. So you have four of the next level VI. So it can become exponential. And so if you have long chains of reentrant VIs with multiple calls at each level, it can be a lot of data spaces.
Okay.
And so shared reentrancy allows you to break those up. And you don't have to make them all shared. but just, like every third layer, if that layer is shared, then it breaks up that exponentialness and it resets it. So you're not creating as many um, copies down below that.
Okay. So I'll turn this into a top points of advice. Sounds like that would be one to use shared reentrancy wherever possible, or at least periodically, to break up the exponential
Yeah.
increase in memory.
To evaluate your reentrancy VIs, looking for where you may be creating more instances than you really need,
Okay.
and use shared reentrancy there.
What are some other top pieces of advice for somebody who's already done the benchmarking and come to the conclusion, I need to better optimize the execution of my code? Are there any other go-to tools or methods that you'd recommend they explore?
That gets back to the, performance and memory profiling that's in LabVIEW, or desktop execution trace toolkit, to look for places where there's synchronization points between things that would otherwise be running in parallel. So that's where you can evaluate, if you are using something like a DVR, a data value reference, am I being slowed down because one place is holding it too long and causing someone else to have to wait on it? Similar
Okay.
things for any of the, you know, data communication things like queues, notifiers. Desktop execution trace can really let you hone in on where those are being weighted on, and see if that's impacting your performance.
So, Greg, how different is what we do under the hood? I know you mentioned earlier that some of the platform-specific optimizations, some happen at deeper, a lot happen at LLVM, but we obviously also target real time. It's another example. And so, are there things that we do markedly differently if we know the code's running on a real time target under the hood?
In real time, the times sequence definitely has additional hooks into the real-time scheduler. The code itself is not that different. The biggest thing is, particularly on FPGA, but it can also be done on real-time, is fixed size arrays. So normally arrays in LabVIEW can grow and shrink as needed. In FPGA, we need to know the size of every array at compile time. So all the arrays have a defined size, and we can take that into account when we're doing the compilation and the allocations. So you can also
Okay.
do that on RT to make sure that you're not introducing any dynamic memory allocation into something that's supposed to be deterministic, because memory managers are not deterministic.
Okay. All right. We've covered a lot of ground. Where do we go from here, Greg? As far as I want to give you a platform to share any other insights that we may have otherwise missed, but also speak to the future, some of the investments, other improvements we're actively working on your team with regards to performance, execution, compiler, et cetera. So anything you can share at this point with the audience about what they can look forward to in the future when it comes to memory and optimization?
There's not a ton going on as far as compilation right now. We are doing more in terms of, well, sorry, not a lot in terms of the performance of our compiled code. We're doing more in terms of the performance of compiling itself. We always want to make compiling faster. We always want to make binary builds faster. So that's an area we're working on right now to,
Okay.
yeah,
Yeah.
to
And
improve those processes.
When we talk about performance, we've been very fixated on how it allocates memory for the sake of running code, but there's also load to edit, how long that takes, load to run, the actual generation of an assembly, and the memory footprint and the time required for each of those. And so we in the context of memory and performance discussions, usually try to specify. Of course, we mainly talk today about execution speed, but as Greg mentioned, we are actively working on, you said, the compile performance, right? And I assume that gets into some of the work we're doing around packed project libraries or PPLs.
Yes. And having a separate cache for builds, because the code that gets generated in a build is a little bit different frequently than the code that was used interactively. So we can't just use the same code. So we have a secondary cache specifically to handle these builds. And also project load time is something we've looked at. We've made some improvements. So hopefully the next release will be a little bit faster.
All right, Greg. Well, thank you for your perspective and your input. I'm sure we'll have to have you back maybe to talk about some of that future work on packed project libraries. We'll figure it out. But thank you, everybody, for tuning in. If you have any questions or comments for Greg or want to learn more about what we do under the hood, feel free to leave a comment below. And as always, be sure to subscribe to the Measurement Lab so you see all the future episodes that we have coming up for you. Thanks, everybody. Thanks, Greg.
Yep. Thank you.